All right, well, cool. I'll get started. So yeah, I'm here to talk about super resolution in JavaScript. I've built this tool. Let's see here. How do I get to the, there we go. I built this tool called UpScalerJS. This is a tool for doing super resolution in your browser. It's built with TensorFlow.js. We currently have models that will scale images to 2, 3, and 4x. Something that I'll touch on in a second is something unique to these models is that you need to train it with a particular scale in mind. So you just need to establish that up front. These are some of the links. There's the GitHub. There's also an NPM. And then this last link is an online tool, an online demo of the tool, which is also the GIF in the right, where you can play with it yourself. So a quick overview. I'm going to give a quick overview of the talk, and then I'll dive into it. Super resolution is the process of taking a low resolution image and turning it into a high resolution one. And there's a lot of different techniques for doing this. I will later talk about how I researched and picked which algorithms to use. I mentioned a little bit about myself, but I have the slides, so I'm going to take an opportunity to do it again. I have a design background in human-computer interaction. I worked as a UX designer for a little while before switching into doing JavaScript and building single-page apps. Now I work full-time at a company called Archipelago. I'm on the data science team. So a lot of my day-to-day work is in Python, which Costas, you mentioned as well. But I am extremely interested in pulling more JavaScript implementations into our work. So the agenda for this presentation, we're going to start with a problem. Whenever I like to embark on one of these projects, I like to sort of have a clear problem definition that we're trying to tackle, that we're not just making technical solutions in a vacuum. So I want to talk a little bit about what this tries to solve. We're going to dig in a little bit more on the nitty-gritty of what super resolution is. And then I'm going to spend some time talking about how you, as a JavaScript developer, would approach the world of machine learning. This part, I may speed through this a little bit because it sounds like Costas, you are familiar with this a little bit, but we can make it more interactive. And then the final part of the presentation, I will break out some code and talk through how this is actually implemented. So the problem is a lot of the time, as web developers, we have very image-heavy sites that we're dealing with. This actually is both a problem I'm facing today as well as a problem I faced in my job two jobs ago, where you'll come up with a design for a new app or website. And it's very image heavy. Images play a big role. But then when it actually comes time to deploy it, the user-generated content that you have is actually providing images that are low quality, or somehow like not of big enough size. And so this can really mess up your design if you're scaling up your images to fill some huge beautiful div. It can look not so great. And so at my current gig, this is one of the challenges that we're dealing with, is that a lot of our clients' images are not of the highest quality. And so a non-technical solution that we have been pursuing is just to ask them for better images, or to try and get images from other places. So like maybe PDFs and documents, or it may go to their original website where they may have the original versions of their images. So if you can do this, obviously this is probably the easiest solution to the problem. Kind of makes the problem go away. But a lot of the time, this is not possible. Either the images that they have are all they've got. Maybe they're older images and they don't have access to the originals, or for whatever reason they don't have high quality imagery. So another solution is super resolution, which is the topic of this presentation. So like I mentioned, super resolution is taking a low resolution image and converting it into a high resolution image. The original image I showed, the original example of this was just was a bit smoke and mirrors. This is an actual output. So on the left, we have the low resolution image, which you can see is fairly pixelated and blurry. And on the right is the high resolution image. Depending on the size of your screen, you may notice the image on the right. It's not a perfect recreation of the image. That is effectively impossible. But it has a lot more detail. It has a lot more fidelity than typical upscaling algorithms that we've had, like bicubic interpolation and things like that. And so what super resolution is it's a technology where we're training a neural network to basically try and predict the pixels that fit in. I'm kind of dumbing it down a little bit, but we're trying to teach a neural network to paint in the pixels between the pixels as you increase the size of an image. And so traditionally, this has been applied on the back end using Python. And there's a number of advantages to doing that. One of the biggest ones is hardware. If you're in a situation where you need the highest accuracy, the best quality images, deploying this in Python is going to be the way to go. You can also run the most cutting edge models that you may not be able to outside of Python. In cases where you may upload once and then display often, then spending more time on the server processing the images is probably less of a concern. But there's also some disadvantages to implementing this on the back end. One is there's longer feedback time. So when a user uploads an image, then that image has to go all the way to the server, get processed, and then be sent back down to the client. This is a big one. This is something we run into. Deployment of these models is always non-trivial, and particularly when you're getting into issues of scale. Having to figure out how to deploy the appropriate GPUs, how to make sure all your Python dependencies are up to date. Depending on how much machine learning you've done, you know that this can be a rather large time sink where you're just spending time trying to make sure that all your dependencies are up to date. When I tried. I really wanted to, this has been sort of a long running goal of mine, is can we translate this technology to JavaScript? And I originally tried doing this about, I think, a year and a half ago or 2 years ago, and I was unable to do it. And so a few months ago, I thought I would give it, take another swing at it, and lo and behold, now it is feasible. And part of my motivation was what I think are these very compelling reasons for being able to run this in JavaScript. One is that deployment problem goes away. And this is actually something I see with a lot of machine learning projects is there's something really magical about just being able to give out a URL and say, like, go to this URL and upload an image, and boom, it works right away. That's really powerful. I think there's more and more tools on the web that let you do something similar with Python, but even so, I think they're not as seamless as being able to run this in JavaScript. And on the other side, as a company, you can cut out a whole mess of headaches if this is running directly on your user's computer. Immediacy is another big one. If you cut out the server processing time, that can be a big win, especially if your users are on bandwidth, have bandwidth limitations. And that's actually also the third one. I think probably the most compelling reason for doing this is to cut down on file size. Depending on the size of your model, if you're using a 4x model, you can take an image that is like a 16th of the size. And that's really powerful. In practice, well, I'll touch on that later in the presentation. But I think this is, for me, the killer use case of this technology is to be able to save on bandwidth. There's also some disadvantages, which I feel obligated to mention. Performance will probably be less accurate than something that you could also run on the back end. It may also be slower than something that you could run on the back end because you're restricted to your users' GPUs. Another potential concern is what kinds of devices your users are using. So if your users are primarily on older devices that may not have the latest technology, that could be a problem. And if there's a range of users, then that could be a problem, which is that. But JavaScript, absolutely first-class citizen for deploying this technology. So I'll kind of skip through this a little quickly. So you maybe, if you don't know how to find machine learning research, most, if not all, is published publicly and is published as these academic papers. They can sometimes be a little bit intimidating to read, but I would urge you not to be scared off by that. One of the websites that I like to use is this website called Papers with Code. This lists research by topic area. So here we're looking at the computer vision, and there's actually a whole section dedicated to super resolution. And so, we can dig into that and we can see how different papers, different architectures compare to one another based on a shared set of metrics. Most of these will publish results against like a shared set of benchmarks. So it's really easy to see the performance. Benchmarks can be a little bit misleading. So for super resolution, the two common metrics are PSNR and SSIM. This is an example of an image that is scoring the same amount of PSNR, but with very different SSIM scores. And I'm not just picking on PSNR here. You could do a similar sort of demonstration with SSIM. And I think that the important thing to note here is that these are they're good metrics for improving a model, but they're not exclusive. You shouldn't sort of put all your eggs in this basket of using these two metrics. And the paper that I ended up going with actually makes this point as well, is that however, these metrics fundamentally disagree with the subjective evaluation of human observers. A lot of the time, a model that is actually scoring a higher accuracy can have a sort of aesthetically less pleasing result. So a little bit more about how I went about choosing an architecture and an implementation. While accuracy is important on these metrics, the absolute best accuracy is not really important because that metric may be misleading. Also, speed is critical. To run this in the browser, it's more important that we have something that is 90% accurate, but is half as, or it takes half the time than another model that may be slightly more accurate, but is much slower to run. And the last thing is that the model has to be compatible with JavaScript. If you've done some TensorFlow.js, you probably are familiar with some of the challenges of converting these models into JavaScript. The blog post, I'm not sure that I mentioned it. I have a blog post on a lot of this stuff where I dig in a little bit more about how you find a model that's really appropriate for JavaScript. But the sort of high-level takeaway is sort of a try and see. Download a bunch of these Python implementations, try and convert them to JavaScript, and see how they do. A lot of them out of the box won't work, for various reasons. I think that's probably the best use of time in terms of trying to find one that's really good. So I ended up going with an implementation called ESRGAN. It had a lot of references. It had a lot of implementations. It did not score the highest of all the architectures, but what really drew me to it was how robust the implementation seemed to be. Like, there were quite a few of options, whereas some of the ones that scored higher, they would only have 1 or 2 implementations, and those might be in PyTorch, which, to my knowledge, you cannot convert to TensorFlow.js. So I ended up going with the implementation by Ideolo. The reason there, I evaluated 3 or 4 of these. This code base was very clean. They provide pre-trained weights. There's an accompanying blog post about how they set up the code. And so, it seemed like a very robust implementation of this particular algorithm. So if you're coming at this as a JavaScript developer, I think one of the challenges is that there's a lot to cover when you're sort of approaching machine learning as a newcomer. And so I think not having to do everything from scratch is really good. Like, you can always go back and do your own Python implementation, or even, you could try your hand at implementing this directly in JavaScript if you wanted to. I'm not sure that would be super beneficial, but if you are, sorry, on the training side, the inference side is implemented in JavaScript. So I think, the point I'm trying to make is we don't need to reinvent the wheel. There's a lot of giant shoulders that we can stand on. Oh, so, and this is the blog post I mentioned. I go into a little bit more detail here in terms of how I evaluated the algorithms and how I evaluated the code bases. So if you're interested, check that out. Let's jump into some code. What do you say? All right, I'm gonna jump out of the presentation for a moment. And, oh, sorry, 1 second. I got to log in here. How's everyone doing so far?
Yep, okay. Following along.
Cool. Any questions so far?
No, I'm I was just running a picture with UpScaler, and it seemed to like my GPU was running at a peak percentage, and it slowed down Zoom. So
Oh
Zoom
no.
was yes, it was kind of looking sluggish, and I was looking at the GPU was like peaking really high, but
Okay.
eventually it finished. So I
Did
have
it?
also an example here.
Great.
And one thing if I may add about upscaling is that I'm using an example of a picture, a photo I took some years earlier. And I think this is one example that we can use upscaling. So I took a picture with a low resolution digital camera about some years ago. And there is no other way that you can upscale or get a higher resolution. So I think that's also a good case for using upscaling. So I don't remember the megapixels on that machine, but it was like on that camera, but it was really like low resolution compared to today's, high-res stacks. So I think this is a nice opportunity for using this kind of software.
Absolutely, absolutely. In a way, it almost reminds me of like colorizing old photos. Like trying to bring them up to speed. I'm not sure. Have you seen folks have done demos where they'll take like old video games and they'll increase the resolution with super resolution of these like old 8-bit video games? Have you seen any of those demos?
No, not really.
Yeah, it's cool. It's like it seems like a really, it's kind of like how Disney remakes their old animated films with like the latest technology. It's like a way of bringing old video games into the present.
That's cool. I'll check it out later.
Yeah. All right. So I'll do this. So the first thing, once you've found your model, you can convert it using TF-JS converter, which is something that TensorFlow.js offers. So if you don't know what Colab is, Google Colab is an online platform for running Python in the cloud. They offer GPUs for free that you can use. You can also pay for them to increase the power somewhat. So here we are loading the model from the implementation, and then we are saving it. And then this is where we're actually doing the conversion here. So it's a Keras model. We are specifying this TF-JS layers model as an export. And then we write it out here. And then if you look here, let's see, where does it write? Right here. So it writes it to this folder, and then I'm zipping it up here. One of the things you can do here is also quantize the model, which I'll touch on at the end as a way of improving the performance further. So in any case, this is sort of the first step for converting an existing model into JavaScript. You have to run it through a tool that will take the Python implementation and make it JavaScript compatible. Once you have that, let's see what happened to Keynote. So once you have that, and I should share these links. You know what? Let me put them all in the chat right now, so you can follow along if you want. How do I copy? Nope. All right. You know what? After this presentation, I'll put them in the chat. So here, so this is Code Sandbox, is an online platform for running code and specifically JavaScript. So we've uploaded the model here, and we are loading it here. You want to load the JSON file, not these .bin files. The way TensorFlow.js works is it will shard the weights. And the reason for doing that, I believe, is for caching purposes. And maybe maybe Costas, you can tell me if I'm actually right here. But I think it has to do with keeping the file size under a certain amount so that the browser can effectively cache the weights. So this is a small little program that I set up. So what this is doing is we're saying load our model, which is here again, get the pixels of the image, and this will return a tensor. A tensor is a multi-dimensional array of numbers. So in this case, it would be a three-dimensional array where you have sort of width, height, and then the depth is the number of channels, so like RGB. We then expand the dimensions, which I won't touch actually, but if you are interested, we can chat about what that means at the end of this. We then run that tensor through the model. We ask it to predict, and then finally we cast that as an image. And so if we run that by hitting upscale, voila, it works. So very little code to make this work, yeah, and it works in your browser. So one issue with this is if we time this, let's just let's see if that does it. So let's see how long this takes. So it took 923 milliseconds, which is not super fast. I think if I were building a site, that's not really what I am looking for. But what's interesting is that subsequent invocations are much faster. So now we're looking in 100, 180 milliseconds to actually do the upscaling. So what's going on here is TensorFlow.js has, well, I don't know, there's this concept called warming up the GPU. And the idea is that TensorFlow.js basically compiles the GPU instructions into your computer's GPU. The initial run of that takes a while. If you are interested in learning more, let's see, I believe if you just Google for TensorFlow.js warmups, there's more information on exactly what's going on behind the scenes. What we can do to get around that is to do what's called warming up your model ahead of time. And it's as simple as sending a dummy tensor through the model. So here, we are constructing this tensor, which again is just an array. We're constructing a multi-dimensional array of dummy data of the same dimension as the image that we are going to pass through it. And as a result, the very first invocation is much faster than the original. So instead of 900 milliseconds, it's 200 milliseconds. One challenge with, yeah.
Kevin, just out of curiosity, can you also time the dummy tensor prediction?
Sure. Let's reload this from scratch. So the dummy tensor, again, took 900 milliseconds, and then the subsequent invocation was much faster.
Okay, thank you.
Yeah. So one of the challenges with this is that this only works if the dummy tensor is of the same dimensions as the image that you're looking to put into it. So for instance, let's say instead of using our image height and image width, we say let's say we have an image that is slightly different dimensions and we run it again. In that case, what is this? Sometimes there's some weirdness with running TensorFlow.js in Code Sandbox. It has to do with how it reloads. So if we're not using a dummy tensor of the same dimensions, as you can see, it still takes a long time. So it's very specific to the size of the tensor that you're sending in. A lot of the time, if you're doing, say, like image classification, this isn't a big deal because you will resize your images before you put them through the model into whatever like expected tensor size there is. But in this case, we don't have a set image size. It could be anything. So, so this is a solution, but we still need a way to give it set sizes.
And you mentioned this is it works only if it's exactly the dimensions of the original image, right?
Yes, exactly.
Okay. Thank you.
Yeah. So the way around that is to, so there's two things here. The other issue is that it's still taking 200 milliseconds for this image. As you increase the size of the image, that will sort of scale exponentially, which you can mitigate to some extent with web workers, but it's not like a silver bullet. You will still, for a large enough image, you will sort of crash the computer. It sounds like, Costas, you already encountered that with the tool as it stands today. So one thing that you will that is commonly done in these super resolution implementations is this idea of slicing up the image, and I have an animation of that. So instead of upscaling a single image, what we can do is basically slice the image into pieces and upscale each one individually. And so what this allows us to do is run an image through and then release the UI thread back to the user on a regular basis. So we're not just taking, 30 seconds to upload a single image and you can't move your mouse. We'll still, for a big enough image, it'll still take 30 seconds, but at least, the UI will be interactive. One issue with doing this naively is it can lead to this pattern of artifacting. And so this is an example where it's really apparent. If you see, like, on the edges where these slices are, it's very obvious that there are lines. And this actually is happening on the edges of a lot of images, but I think it's a lot harder to notice on the actual edges of the image. It has to do with how the model is figuring out which pixels are next to those edges, and that's sort of what causes that artifacting. So one way we can get around this is basically to add padding to our model. So instead of taking each chunk, we say, like, give me a little bit extra, and then you concatenate the image by slicing off those pixels that you don't need. So they still have those edges and those artifacts, but we can get rid of them. This also has the very nice side effect of allowing us to have a consistent image size that we can send through our model. So long as you set the patch size smaller than your smallest image that you would expect to receive, we'll always have a consistent image, like a consistent square image that we can send through our model. So we sort of hit two birds with one stone. We both allow for a snappier UI, and we also tackle that warm-up issue that we were seeing in the last one. And so this last link that I wanted to show, this is using don't know what that means. this last one is using UpScalerJS, this tool. I'm sorry, no, it's not. Scratch that. This is just doing all of it in the browser. So the code that is actually doing the logic, the slicing, is right here. So it's a little math heavy, but you know, hopefully you can follow along. And what we can do then is actually look at the output. So this is a little tool that I put together that kind of lets you just play with the specifics. So this has no padding. You can see there's like pretty obvious artifacting here between each chunk. But what we can do is increase the padding, say to, I don't know, maybe 4. And then the padding goes away. I mean, sorry, the artifacting goes away. Because now we're slicing off that that unsightly edge. So, and this is made with React, which hopefully you are familiar with. So let's go back to the presentation. So there's some other improvements that I'm sort of looking to get into this tool. At the beginning, I touched on quantization. I think this is something that I'm applying to all the models that are in this tool. What quantization is it's sort of like MP3 compression a little bit. I probably should have mentioned this up front. A neural network is a series of weights. Weights are floating point numbers, and they can have some degree of precision to them. So I think the default is 30. I'm not sure exactly. Don't quote me on that. So if you are, let's say you're looking for a model with really high accuracy, you wouldn't want to quantize because you're losing the ability to make really fine-grained, accurate predictions. In our case, where we're doing this upscaling, you know, if a pixel is slightly more blue or slightly darker than it is in real life, it's not really going to be noticeable. And so what I've found is that basically the maximum amount of quantization, which is 8-bit, works really well. It also makes the model much smaller to download. And so this is a process that is applied at the time of conversion of the Python model. And so this is an argument that you pass directly into TF-JS converter. Model pruning is another big one. And this is something that is new to me that I'm still learning about and trying to explore. This is basically an operation where while training, you try to find the weights, you try to find the parts of the neural network that are not really contributing much to the overall prediction. So a lot of the time these weights are either 0 or they're close to 0. What you can do is you can just cut them out entirely. And you know, I've seen models where you can cut out 90% of the model. That's like how much there is like extra neurons, and those savings you get, you know, in terms of the inference of the model. And so this is really relevant to JavaScript in the browser. If we can cut our model by, you know, down, I mean, 90% is probably much, but even if we could cut it by 50%, you know, trim out 50% of the neurons, that would be a huge speed up. So this is something that I'm looking at right now. All the techniques I've seen, this has to be applied during training, and so all the models sort of need to be trained from scratch. So this is sort of an ongoing area that I am looking at. And then the last one also connected with that is better data or domain-specific data. So, you know, training on specific data sets often will yield more performant models for your specific for your specific use case. So for instance, like if I show an example of that, there's a couple like sample images here. Let's see. So this is the baboon that we've been looking at. You know, and it works decently well. There's some, you know, artifacting on the eyes, but it's certainly higher resolution, you know, than the original bicubic one. But as we get into other areas like illustration is one where you know, this actually looks decent. But if I look at the original image, let's see, where is it? You know, these lines are a lot sharper than we end up getting in the model. Honestly, I'm not sure that a model would be capable of recovering this because it does look, you know, the original image is fairly washed out. There's not much detail there to recover. So I actually think the model's doing a pretty decent job here with what it's got. But, you know, faces is one, I think, where, you know, we could see some really big gains from training on a specific, you know, a specific face data set. Because right now it's trained effectively on like a general image data set of just, you know, all kinds of images. It's a website, sorry, it's a data set called div2k that we're using for these models. And so, you know, there are face specific data sets, there's illustration data sets. And so, you know, I really do think training on that specific data set will give you a big win. And so, and that's something that I'm looking to do is to sort of provide those models in directly in this tool. And, well, we saw this. And that is it. Oh, that's it. That is the presentation. Here are some links. This is a link to my blog where I go into a little more depth on like how you choose a model and how you convert it to JavaScript. And then down here are links to the tool if you want to check out the GitHub, the NPM link, or this tool that I'm playing around with. You can do that there. So yeah, thank you. This has been a lot of fun. I think we probably have time for questions if we want to dig into anything.
Yeah, we do have time for questions. The floor is open for questions.
Costas, all you.
Yes, so I have a couple of questions. So the first one is, what kind of machine are you using? Because I'm training the same images and I see like my speed is way slower in the conversion. So just out of curiosity, what kind of machine are you running on?
I am running on a MacBook Pro this year.
Ah, okay. Okay, I'm a few years before, so yeah. I guess, but it. I mean, the conversion on your machine was almost instant. It's taking some time on my machine. So,
Yeah.
another question was like, I think you mentioned that you're using it in production or on the.
Not yet. You mean mean at my company?
Yes.
Not yet.
No.
Yeah, we're looking at it, but no, it's not in production yet.
Okay, and I think you mentioned about different models. I think they're available in the demo, like where it says guns and
yeah.
So we can also
yes.
It loads these models and then you can rescale it with different, right? Yes.
So these two are directly coming from the repo that I shared by Ideolo. So those are the pre-trained weights that they offer. And then these div2ks were trained by me. So actually, yeah, when I said this was trained on div2k, actually that is true because I believe Ideolo's models are also trained on div2k. It's yeah.
Mm-hmm.
Yeah, so they trained it on div2k. Actually, one thing that I didn't mention, that I totally forgot to talk about, is that one of, so here, let me just, I'll show it with code. So everything that I showed was the RDN model, which getting very technical, that was the original super resolution model that ESRGAN was designed to improve upon. There is also an RRDN model, and that one did not convert to JavaScript easily. The sort of TLDR is that to make it work, you need to implement custom layers. And I'll show you specifically the back and forth. Where is it? ISR models. Yeah. So there are these custom layers that this model is implementing. I believe these are explained in the paper for ESRGAN, specifically pixel shuffle and multiply beta. TensorFlow doesn't offer these natively because these are custom functions. And so what you need to do is effectively re-implement them in JavaScript. And the process for doing so, if you are interested, is in the repo at source models ideolo GANs. And so you can kind of see, this is multiply beta, this is multiply beta. You can kind of compare and contrast. And then these custom layers need to be registered with TensorFlow under these names for them to be picked up by the model. So without these, the more performant GANs model, the RRDN model won't work. So this is something there's not a lot of documentation on how to do this. I kind of was banging my head against the wall. So hopefully this is helpful to somebody in terms of trying to translate this. I believe like you need all this stuff like the class name and the constructor, but really the actual code that's doing the logic is generally in this call method. So yeah.
Would it be okay if you can share the links of the code sandboxes too on the chat?
Yes, I will do that right now.
I will also send the links after this talk to all attendees.
Great. Okay. So there's the first link is the bit.ly link is to Colab, Google Colab. Then the other ones are the various code sandboxes, and then the rest of the links from the end are there. So link to my GitHub, Twitter, and then also the bottom is linked to the tool and the GitHub for the tool. And I will also share this if you are interested in custom layers. I'm not sure if you are, but I'll share these links as well if you are interested in comparing the two.
Kevin, great presentation. Sorry I hopped in a little late. Had a question, well, two questions. Primarily, is the recording of this meeting going to be available to us? I believe Bhaskar just mentioned he's going to be sending something, but is that going to be the recording of the beginning?
Yeah, I'll be sending the recording as well, along with all the links which are shared in the chat.
Okay. Yeah, awesome. And then also just a general question. So I'm relatively new to TensorFlow and its uses. I'm aware that the biggest pro of the incorporation of TensorFlow or the image model would be to kind of reduce the usage of memory by images. But what would be a drawback in your experience from incorporating it in your stack or in your implementations?
Well, one drawback is what Kostas just mentioned, is that if you're not the discrepancy between hardware can be a real issue. So particularly if like I'm running this right now on a 2020 MacBook, MacBook Pro, and the speeds are quite decent. But as you sort of go farther away from that, you are potentially looking at big speed impacts for your users if their hardware can't keep up. The other challenge is that if accuracy is very important, then you're better off running it on the server, because you are somewhat limited by in terms of like how much hardware you can throw at these things in the browser. But I think it is balanced by the cost savings. If your user does have a capable enough machine to run this directly on device, then then you can save a lot in bandwidth just by doing these upscales right on the client.
Awesome. Yeah, that definitely makes sense. So, from your experience, are there any ways where you can kind of potentially mitigate that? Specific ways of implementation, or some things you found that kind of helped with the differences in hardware and their capabilities?
I don't know that there is a specific way to mitigate the hardware. What I do think is focusing on performance in general will sort of lift all boats. And like particularly like the model pruning, for instance, like if we can cut these models down to 50% of their size or even more, that will make a MacBook Pro 2020 like extremely fast. And then like a device from a few years ago will also see an improvement in speed. I think that if it is important that all users have a consistent experience, then you're probably better off running this on the server, because that's sort of the only way to guarantee that everyone has access to the same kind of power. I think it's very use case dependent. I think it really depends on what your users are looking for. I mean, in a lot of cases, it may be okay if it takes 2 seconds on an older device, but 1 second on a newer device, that may be okay as well. But yeah, I think in general, improving the performance with quantization and pruning will sort of lift all boats by some equal amount.
Yeah, definitely. Okay, thank you. Yeah, I appreciate the clarification with those.
Totally.
And can I ask something?
Yeah.
Just a quick question. Any other projects you're currently working on with TensorFlow.js?
Oh yeah. Built this tool. Let's see where. Built this tool called ML Classifier, which is sort of it's inspired by Xcode's ML Classifier, where you basically just drop in a folder of images and it will spit back with a classifier that will automatically classify your images. So this is something that exists. Here, I can share this in the chat. And there is there's a GitHub. It's on GitHub here. I haven't done a lot with this. I had thoughts that I would do an implementation of this for text, but I have not done that yet. I think those are sort of the main projects that I have for TensorFlow.js. I have been doing a lot more Python in the last few months. I'm very eager to get back to writing JavaScript and machine learning. I'm kind of hoping this is a good sort of wedge to get back in there.
Great, thank you. And do you train your models on Colab or some other way?
So I built a GPU I built a GPU box in 2017. It's a little bit rusty at this point in terms of the latest models. I have used Colab for training. I think for the experiments that I've been doing with UpScalerJS, I am using Amazon GPUs on Amazon, just to kind of speed things up and get access to the latest and greatest. Yeah, for a little while actually, I was paying for Colab to try and get access to like the really, if you pay, they're sort of opaque about like which ones you get, but if you pay, you kind of get like priority access to better GPUs. But I'm no longer doing that. Kind of moved down from that.
Okay, thank you.
Yeah.
Cool. If you don't have any further questions, I think we'll call it an evening. Thank you all for joining with us. Thank you, Kevin, for going over everything about UpScaler and all your GitHub projects.